I always believe in answering questions that are given to me, and these are good questions that are given to me by my YouTube audience. And I had a pretty good question, and I'm going to answer today. And it was from Idster7, okay? So I am answering your question, Idster7, and I hope you bear with me because this is kind of complicated. But when Euclid decided not to put a certain part of the proof in there, he was kind of hoping you guys would solve it. But in this case, you don't seem to be able to solve it, so I'm going to solve it for you. We're going to go back to Euclid Book 1, proposition number 47, and I'm going to solve this for you so that you can kind of get an idea of what's going on. All right. Now, hopefully you'll agree that angle BAC, which this is B here, this is A here, and this is C here, is 90 degrees. That was part of the proof. And if you don't know what I'm talking about, the rest of you need to go back to Euclid Book 1, proposition number 47, which ended up being in 6 parts, and review all 6 parts. Because BAC is 90 degrees, and that was pretty much part of the given part of the proof. Okay? Now, we also know that BAG, here's B, here's A, here's G, it is also 90 degrees. And if you were to add the number of degrees in BAC and BAG together, you would get 180 degrees. Now, since we also know that BAC is 90 degrees, and we also know that CAH, here's C, here's A, here's H, right across here, CAH, it is also 90 degrees, then if you were to add the number of degrees of angle BAC and CAH together, you'll get 180 degrees. Hopefully, so far, you're following. All right. Now, let's go find another angle here. We have an angle called DBC. Well, here's D, here's B, and here's C. DBC. It's part of a square. And I bet you're probably sitting there going, well, if it's part of a square and the angle is DBC, it most likely will be 90 degrees because angles and squares are 90 degrees. If you don't believe me, you can go back to Euclid Book 1, proposition 46 and see for yourself. All right, now we have another angle. It starts at F, goes down to B, and comes over here to A, and it is also 90 degrees. Why? Because it's part of a square. Okay. So that makes angle DBC, DBC, the number in degrees in angle DBC, which happens to be 90, equal to the number of degrees in FBA. FBA. That's also 90 degrees. Now, let's go over here. We have another angle, and it's called ECB. Here's point E, point C, point B, and it is 90 degrees. Why? Because it's part of a square. Okay. And then we have another angle called KCA. KCA. And because it's part of a square, it's also 90 degrees. All right. Now, if we were to take angle FBA, FBA, and ABC and add them together, the number of degrees in both of these angles would be exactly the same as if you were to take angle DBC and add ABC to it. So DBC, which is 90 degrees, and CBA, or ABC, whichever one you want to call it, is some other type of degrees. You add that together, and it's going to be the same number of degrees as if you were to take FBA and ABC and add them together. Okay? Following good so far. Same type of deal over here. If you were to add the number of degrees of angle ACB to ECB, you would get the same number of degrees as though you were to take angle KCA and add it to ACB. Alright? Follow me so far? Alright. That means that angle DBA, well, we have an angle, it starts at D, goes to B, goes to A. It is equal in size to angle FBC. Okay, we established that in Euclid Book 1, proposition number 47. You can review that for yourself. But now we're going to show you another angle. ECA. Starts at E, goes to C, comes over here to A. And it's going to be the same size as KCB. K here, CB, K here, C here, B here. So ECA and KCB, these two angles right here, are going to be exactly the same size. Alright, now, we said that DB equals BC, and that's because it's part of a square. And as you know from Euclid Book 1, proposition number 46, that if you have DB and BC and they're two sides of a square, they're going to be equal in size. Likewise, if you have lines CEC and CB, they're going to be equal in size. Why is that? Because they're two sides of a square. Alright, FB and BA are equal in size. Well, here's FB and BA, they're equal in size. Well, we can also say that KC and CA are equal in size. Okay? Now, because angle DBA is equal in size to FBC, and angle KCB is equal in size to ECA, what you have on both of these is the side-angle-side theorem, which goes all the way back to Euclid Book 1, proposition 15, and back even before that. And because of that, okay, and I'm not sure whether it's 15 or whatever, you can look it up for yourself. Just go back to Euclid Book 1, proposition 15, and go back a couple of theorems before that, and you can find it. Okay? This is what we call the side-angle-side theorem. And since we have two sides of equal size and an angle of equal size, then what happens is that triangles KCB and ECA are equal in size. Okay? And then that makes all the remaining angles in those triangles and all the remaining sides in those triangles equal in size. And because of that, that should answer your question. If it doesn't, leave me another comment and I will happily go through the rest of it for you. But I think that should answer your question pretty good. Alright. I will tell you more in a future video. Thank you very much, Idster7, for writing me. This was a very good question, and hopefully I gave you a very good answer. I know I was kind of quick about it, but at least now you know the answer. And it was a good question. Thank you very much. I'm glad, and I hope you ask me more questions, because I like questions like this. I really do. I will tell you more in a future video, so stay tuned.